So we're almost good to go. We've got voice, maybe slides will come, or maybe I'll present slides from someone else. Because apparently my 1 megabyte PDF can't load. So don't get disturbed by what's happening behind. Luckily my first slides weren't containing any code, and by the time I will have to talk about code, maybe we'll have the slides. So thanks everyone for attending this session. How many of you already have used the Android NDK? Whoa. I mean, I've made this presentation in many countries. Ukraine wins. Just win. Really, that's really cool. And so then I may do the advanced parts even more than usual. Thanks. So for those who don't already know the NDK well, the NDK is what you use on Android to integrate C, C++, even assembly code into your Android application. So the NDK by itself, it's a big package with toolchains, scripts that allows you to build native libraries. And when I say native, it's binary libraries that are shared objects you can load at runtime for your Android application. So this toolchain is available on, of course, on Mac, Linux, and Windows, and the latest version is R10C. So before it was really a big package, a zip file, and now it's a self-extracting zip files. That's a big change. Not. So while the indeterminate loading circle is doing stuff behind, I can also tell you that the NDK is something Google does not recommend to use. It's explicitly stated on the web page when you download it. It's for a simple reason. It's because even if you succeed in making a library, it's loading, you've tested it on one device, it may crash even more than your Java. I mean, and when in Java you can catch null pointer exceptions from just exceptions from everywhere. When it crashes inside the native libraries, usually it's a segmentation fault and your process is killed and you're really dead. So Google recommends not to use it because it can lead to more complexity, more crashes. So you need to use it correctly. And and the other problem is the documentation regarding NDK is not that good. So it's very important to know what you're doing when you're using the NDK. And that's a bit what my talk is about, when it will have loaded. So many applications are using the NDK. In fact, if you look at the top 100 or top 300 applications on the Play Store, around approximately half of these are using the NDK. So games are the first use case for NDK usage. If you want to write cross-platform code, HTML5 is maybe a solution with a web view. But the most common solution is OpenGL code that is cross-platform, and you can compile it in C for many targets. And usually I'll demonstrate, I've made an application on the store that allows you to analyze what the other applications are doing with the NDK. So just to inspect the shared object libraries that has been made with the NDK from other applications. So if you look, for example, at Facebook, Dropbox, Twitter, all of these at one point or another are using the NDK. So for Facebook, it's mainly for handling the memory behind the application when you load images. So they do it in a really efficient way, more efficient than what they could do with the Java, at least the Java APIs that are available since Android, early Android. Oh, long time I haven't seen these slides. It's loaded, that's so cool. And I can even talk about 2 sets of slides at the same time. We're getting there. Oh, thank you. So, if you want to blame me about the start of this presentation, but you can reach me on Twitter, ph0b, and destroy my blog with bad comments on ph0b.com, even if it's not my fault. So I already talked about the first slides, and if someone just scroll a bit, it would be great. Yeah. So when you use the NDK, you can't. If you will not use the NDK because, yeah, I'm a C++ developer, I want to do only C++ in my life, Java, and that's not what you can do on Android. I mean, you can avoid writing Java on Android, but you can't avoid using Java on Android. What I mean is, when you want to do only C++ on Android, you will still have to make calls to Java APIs, because all the Android framework, it relies on Java. So all these set of APIs you may already know from the Android SDK, all of these are only available for Java. And that's all these API, you can call these from C and C++, the same way you can call C and C++ from your Java. So this system is called the Java native interface. And that's not something really specific to Android. The Java native interface is part of standard Java since long time ago, when people were just doing server applications or desktop applications with Java. So all the Android APIs, like what you use to handle views, notifications, providers, and everything, they are all SDK APIs. And you still have NDK specific APIs, for example, for direct access to sensor. You've got OpenGL ES, of course. You've got OpenSL for sound. And all these APIs are quite restricted, and you can find only APIs that really make sense to the NDK. And most of the time, if you want some Android-specific stuff, you'll have to use Java. So in general, what you do when using the NDK inside an Android application is you've got your Android application, mostly written in Java, and you write a part of the implementations of the methods of your application in C, C++, or assembly. And you use the Java native interface to call these implementations from Java. Or for the specific case of a game, you will just call the Android APIs using JNI or in Java directly to instantiate just your OpenGL ES view and do all the rest in C, C++. The biggest use case for using the NDK on Android, aside performance, is code reuse. So having really your code you can reuse on multiple platforms, and not only your code, but really well-written libraries. I think, for example, about, this one would be on purpose, but think about a library that would be that makes you able to load PDFs. That's kind of code that you wouldn't find just written entirely in Java. Usually there are some, it's C, and it's compiled for many platforms. And in this case, if you want to render a PDF in an Android application, unless you're targeting MinSDK level 21, I think we still have some time before you can do that, you'll have to rely on third-party libraries, and they will be native. So, but if you want to reuse an existing code base, first of all, you need to know that Android is it's not always that portable. Because on Android, you don't have the standard C library. You've got Bionic that has been thought more for embedded platforms like Android. So with Bionic, you lose some parts of pthreads. You don't have shared memory segments because Android has binders. That's something different. So there are still some things that aren't there. And overall, since all the system is different, you can't really reuse a binary that has been compiled for 32-bit Linux and directly use it on Android. You almost always need to recompile. And to recompile, you need the NDK. Same for C++. There is C++ support inside the NDK, but by default, almost nothing is there. I mean, you can have objects, and that's pretty much it of C++ you can use by default. But already inside the NDK, you can specify that you want to use other specific C++ libraries, and you'll be able to have, for example, exceptions and access to all the STL that is not even available by default. So we've got many different C++ runtimes available. And to use this is just a matter of setting variables inside your makefiles. I'll talk more extensively about it later. So first of all, to use the NDK, you need your sources. You will put all these sources inside a folder inside your Android application project. This folder is called JNI. So under this JNI folder, you put your sources and a makefile called android.mk. That's the makefile that will be loaded by NDK build. So NDK build is the script that is using the NDK to compile and create these .so files you will load later on. So all your C and C++ implementation is inside the JNI folder. And inside your Java, you'll declare the Java method you want to implement in C and C++ as native. So with a native keyword. And to declare you want your library to be used for this implementation, you'll need to load it explicitly. So you can do this during inside the static block by calling system.loadLibrary and the name of your library. And when you do that, the native library will be loaded, and the implementation that you will have done in C and C++ mapped to your native declared method. So during runtime, here is what's happening. So when you load your application, your Java classes are just loading. The static blocks are executed. So your native library is then loaded. And once it's done, it's done. And later on, when you call the Java method you've declared native, then you'll be executing Java code. And when it's reaching this native declared method, the runtime will directly call the implementation in C++. There is no implicit threading or anything. It's just the runtime is executing Java code, and then it's reaching native code, it's executing native code, and returns to Java, and so on. So that means if you have a really complicated and lengthy task, you need still to use threads. So you can instantiate threads from Java or from C and C++. But in any case, everything is handled by the Android runtime. So you don't go outside of the sandbox to do nasty things. This will not happen. So to declare your implementation in C code, you can follow a standard JNI pattern. So for example, if you declare this method, string from JNI, that is just taking no arguments and returning a Java string, declared as native, you can define its implementation in C and C++ by setting the method name to Java, then the package name with dashes instead of dots, then the name of the class where the native method is, and finally the method name, and then two arguments. So one is the JNI environment, I'll talk about it later, and the other is a reference to the Java class or object, if it's a static method or not, so a J object. I went way too far. What happened? Don't worry, we'll go there gradually. NDK is quite complicated topic. So this name is easy to mess up. So what you can do is call Java H from the Java development kit to directly generate all the method headers you then just need to implement. So you set the native keyword in front of the methods you want to implement in C, and then you compile your classes, and then you call Java H on it to generate a header with the proper method prototypes. Then you can write your implementation. And the last part is the Android makefile that you need. So it's classic makefile, and you've got predefined macros that will help you just tell the NDK what do you want to compile. So the smallest Android.mk you can have, so main Android makefile, is the first 4 lines at the top. So you're just including the macro clear vars to clear all the NDK variables, NDK specific variables. Then you define local module, that's the name of your library. You will load the exact same name from Java. And then the list of SRC, the list of source files that you need to compile to generate this library. And finally, a final macro you include, always build shared library. That's what tells the NDK to create your library as a .so file. So that's the file you will load from Java later on. You've got other predefined macros you can use instead. So for example, you can build a static library. So this will build a .a that can't be used directly from Java, but that can be used from another .so file. And when you do that, you build a .so or .a that is to be reused by another NDK project. You need to redeclare part of a makefile as to reference this project. So, and then you use pre-built shared library to declare an already built .so or .a file. And there is a second makefile that's not Android.mk, that's application.mk. So the difference is inside application.mk, you only define variables. There is nothing to be executed. And application.mk is for the whole application. So when you use the NDK, you compile your library against several platforms. So ARMv5, ARMv7, x86, now also 64-bit targets. So each time you compile for a platform, and usually you compile for several, Android.mk is executed. So you can script something that will build something different for each target. And application.mk is for defining variables that will never change across all these compilations. So for example, the version of GCC you want to use, the minimum, your target API level. And also to define the CPU architectures you want to build against. So by default, you can build for all architectures. And so now there are 8 different architectures, from ARMv5 to MIPS 64-bit. So when you work with the Java native interface, so when you do your implementation in your C, you handle Java types. So the primitive types are like the C types you know, but the important thing is they've got a fixed size, because an int is not always the same size for all the CPU architectures you're targeting. It's important to have consistent types you can use. Because if you return an object that hasn't the same size on your native side to Java, it can lead to some terrible things. And what you manipulate also are the Java objects. So all what you manipulate from your C implementation that are from the Java world, they are only references to Java objects. So you get inheritance here. So the main thing you handle is a JObject, and you can also have JString, JClass, JArray of the primitive types we saw before, or even JArray of objects, and JThrowable that are exceptions, Java exceptions. So you can't build yourself from C a Java object. What you do is call the JNI environment. Remember that's the first argument you get to your method in C. So you ask the JNI environment, that is the Android runtime, to create these objects for you. And that also means that all these Java objects, their memory is still handled by the Android runtime or Dalvik. So what you get are references to this, and they can still be garbage collected at any moment. Or even their memory can be compacted and moved, and so on. So for example, you can ask the GenAI environment to create a Java string for you. So this one is really simple. You call env, so that was the GenAI environment you got as argument, and you ask him to create a new string UTF. So there is little difference here if you're doing your implementation in C or C++. So in C, you don't have any objects, so you need to call the environment this way by passing again the environment to the function. And in C++, it's directly an object. But otherwise, the API is totally the same. So there are some limits regarding the number of objects you can handle on from the Java. And sometimes it can be as low as 16. So if you've got a big loop and instantiate all the time new strings, you create new strings and new strings and new strings. Each time you call new to GenAI environment, you get a local reference to the object. And all these local references, they are counted. And that's only when the execution returns to Java, then the objects, your local references are just deleted, and the garbage collector can collect everything. But the number of local references you can handle at the same time can be as low as 16. Sometimes it's more, but it can be really low. So you need to call explicitly delete local reference to keep this number as low as possible. So to access the memory from Java objects, it's slightly more complicated. Here it's again for a string. So you've got several methods. You can get elements that will give you direct access to the memory you want. Sometimes it gives you already the pointer to the real memory. Sometimes it gives you a copy. But in any case, you shouldn't really do modifications directly on this. And you can also get a region that will always provide you a copy that is safe. You can already do whatever you want with it. So on the Java methods, so new string UTF is quite simple because it's string. You use it a lot, so they put an explicit method from GenAI env to do it. But overall, you can just call anything you want, as long as you're okay with writing 8 lines of code to do this. So first of all, it's like when you use reflection directly in Java. You need to specify the full package name and method you want to access to, and then get access to the methods, and then finally execute it. And there is one specific you need to specify is the method signature. So these are specific signatures from the GenAI language. After sometimes you can get used to it, but you can also directly get these signatures using JavaP program from the JDK. So the convention is between brackets, you've got the arguments types and then the return type. Regarding exceptions, you've got 2 types of exceptions that have nothing to do with each other, the Java exceptions and the C++ exceptions. Everything that is C++, it will stay in the C and C++ environment. So if there is an exception and that's not catched, your C will crash and then your Java will crash. So what you need to do is ready to catch everything inside your C and C++ implementation, and if there were already failures you could not handle, then you throw a different Java exception. So only Java exceptions will be catched by your Android code later. There is no automatic translation or anything. And when you throw a Java exception from your native implementation doesn't stop there to return to Java. It's only at the end of the execution of your native implementation that it goes to Java and the exception is thrown. So that gives you some time to clean everything up. And you can also handle Java exceptions. Same here. If a Java exception happens when you execute native code, You can handle it using exception clear. But if you don't, nothing will happen. All your next calls to Java will also fire exceptions because you should have handled the first one. But your code will continue executing until it goes back to Java, where the Java exceptions will be thrown. And usually it's too late. So when you call NDK build script from the NDK, it generates all your libraries. And if you set app ABI to all, it will compile all your library inside all the under the libs folder of your Android project. So once it's done, you've got your .so file inside ARMY ABI v7a under libs and so on. You package it, everything goes into the APK and under the lib folder. And then if you've got one APK that's compatible with all the architectures, you can just push it to the store. And sometimes it's a bit too fast because now if you compile to all the target architectures, you've got 8 times the same file, but a little bit different. What you can do then is to have one APK per CPU architecture for the Play Store. So this will help keep your APK size really low. But there is one thing you need to take care about, it's the version code of your application. You need to have one different version code per CPU architecture. And the higher one needs to be for the x86 and x86-64 versions. Because we've got many Android devices running on Intel CPUs, and these devices are x86 based, but they also can run ARM v5 and ARM v7 codes through an emulation layer. They are fully compatible with everything ARM, and they can run these binaries. That means they are compatible with both the ARM APKs and the x86 APKs. And the store will give the one with the higher version code. To upload multiple APKs on the store, you just need to switch to advanced mode and upload your several APKs. Then your interface will change. You'll see all your APKs each time with the version code and with what changes between the APKs. So in our case, the native platforms you're targeting. So I'll skip the debugging part since we're a bit late. For performance, you can also tune compiler flags. It's the next slide. Through the local cflags variable. And also you can switch the GCC version to a later one, because by default it's 4.6 and it's quite old and not that efficient. And also, if you are using Android Studio, you may have figured out that there is no real C or C++ code editing feature, but there are some NDK support inside Gradle. And it's quite efficient, actually. I write a lot of NDK stuff, and I still use Android Studio as my main IDE, even if it's only for Java code editing, because Gradle is really useful. Now with Gradle, you can really generate one APK per CPU architecture and compute the version code really easily, and it's all built in. So in like 4 lines of Gradle, and not hacky lines, I mean real configuration that's okay, and that's called APK splits. You can generate one APK per architecture with the right version code, and then they're just ready for upload to the store. So that's called APK splits. And if you just need to integrate .so files, because your NDK library is done, you will never touch it again, you can directly put your .so files under a folder called GNI libs, under subfolders named against each architecture, and they will get integrated inside your final APKs. And you still have the feature for splitting the APK for each architecture. So sorry for the rush in the end. We did not have much time. You can reach me for questions anytime during today, during lunch. And one last thing, that's on the slide, that's behind, under. With Android Air, so there is big switch from Dalvik to Arch runtime, and everything that was still okay to do with Dalvik regarding the NDK that wasn't crashing, even your code wasn't well written. Now with Android runtime, it has like 10 more times to crash. Because the Android runtime is moving objects during runtime and memory, so if you've got references to objects that have moved, that can be bad, also in between threads. So if you've got NDK, if you're using .so libraries, you really need to test your applications against art. So, thank you.